Until now, we've focused on single-valued functions. Let's look at multi-valued functions. And let's start with a particularly simple one. Let's look at f of z equals to the square root of z. We saw that we have two roots here. So if we say that z equals to w squared, we have two roots. We have that f is equal to plus modulus of w minus modulus of w. And in fact, there's another way of writing it. We could have written it in this way. F is equal to modulus of w e to the I k pi, where k can take the values 0 and 1. Okay. Now, we have this function f of z, and let's think of what happens if we move this function f of z around a circle in the Argand plane around here. Okay, so we start off with it over here. We start off it with over here, and what do we have? We have that f of 0 is equal to 0. Sorry, f of 1. So we start here, and we have that f of 1 is equal to, what is it? Well, let's just write it out. That's f of e to the 0, okay, over 2, or e to the 0, which is e to the 0 over 2, which is equal to 1, okay? And now we move this around, and we go all the way around, and where do we end up with? Well, we end up with f of e to the I 2 pi, which is equal to e to the I 2 pi over 2, which is equal to e to the I pi, which is equal to minus 1. In other words, when we go around this closed loop, f won't go back to its initial value. There's a discontinuity along here. And this happens for any loop that we do which encompasses that point over there. What we say is that z equals 0 is a branch point for f equals z to the 1/2. Now, that's true of z equals 0, but what if we'd chosen z equals 1? What happens there? Is that a branch point? Well, let's consider a small loop around. So again, we've got this, we've got 1. Let's consider a small loop around there. And so let's write that out. We've got z equals 1 plus epsilon. That's just the radius of the loop, e to the I theta. And if we plug it in, what do we get? We have f of z equals 1 plus epsilon e to the I theta to the 1/2, which we can Taylor expand. And what does that give us? That gives us 1 plus 1/2 epsilon e to the I theta plus all the higher order terms. I'm not going to worry about the constants of the Taylor expansion. I'm just going to write down as Cn e to the I n theta epsilon to the n. Okay, but look at what happens. As you can see, when theta goes round from 0 to 2 pi, this always goes back to the original value. In other words, f of z always returns to the original value. There is no discontinuity if you go around z equals 1. In other words, z equals 1 is not a branch point. Now, there is a way of taking into account that functions can be discontinuous due to the fact that they are multi-valued. And that way is to put in a roadblock to prevent us from going around the closed loops that lead to discontinuities. So again, let's consider the example we had. And we say that this is a branch point, and we normally put a cross like that. And we can put up a barrier just to stop any loop crossing that line that starts at that line and going over. So normally what we do is we do a squiggly line like that. In other words, we don't allow, and this line goes out to plus infinity. In other words, we don't allow any loop that will cross that line. We're allowed to do loops that do whatever we want as long as they don't cross that line. Okay, and that's what we call a branch cut. We put in a branch cut to prevent this multivaluedness hitting us in the face. And if we do that, f of 0 will be equal to f of 2 pi on any closed loop we can consider. Now, we could have considered that loop, we considered this loop going from 0 to plus infinity, but we could have considered that loop going anywhere. In other words, we could have taken that loop, that cut going in that direction. We could have considered that cut being some wiggly line that does that as long as it goes out to plus infinity. Okay, as long as it prevents the loop for ending up, as long as it prevents any loop from closing and you feeling the discontinuity. So an exercise might be that you try and look at what happens in this case and you start with a loop and it goes this way. Or in this case, you start with a loop that does something like this and then comes back over here. You would see that if you didn't have that branch cut, you would get a discontinuity. But any loop that closes around that branch cut is okay. Consider now a slightly more complicated example. Let's look at f of z equals square root of z squared minus 1. Now we can factorize this function and we get z minus 1, square root of z minus 1 times square root of z plus 1. And immediately we can see that it has two branch points. We have a branch point at z equals 1 and a branch point at z equals minus 1. Just to check, let's look at a closed loop around z equals 1. So let's take z equals 1 plus epsilon e to the I theta, okay, and let's see what happens to the function f of theta. Well, you get that it is equal to square root of epsilon e to the I theta. That's what will come out of this one here. And then the other one will give us 2 plus epsilon e to the I theta, okay, which we can now massage a little bit. And what do we get? We get square root of 2 epsilon, square root of 2 epsilon e to the I theta over 2, and then we can Taylor expand what's in there, and what we get is 1 plus epsilon over 4 e to the I theta plus. Now this bit is okay, this doesn't bother us, but this, it's pretty clear what happens. If you go, as you go from f of 0, you'll get one thing, which is square root of 2 epsilon. F of 2 pi, what will it be? It'll be square root of 2 epsilon e to the I pi, which is minus square root of 2 epsilon. In other words, it's very clearly discontinuous. It is a branch point. And the same is true about z equals minus 1. So, given that we find these discontinuities when we circle either z equals 1 or z equals minus 1, we need to conjure up good branch cuts. So let's just write this out again, draw this out again. We have it here, we have it here, and one possible is to just do what we did previously. In this case, we would have a branch cut that goes from 1 to plus infinity and from minus 1 to minus infinity. And any closed loop that doesn't intersect these lines is guaranteed to be continuous. But another interesting possibility is if we considered the following case. Again, we have these 2 points here, minus 1 and 1, and we link them like this. Okay, well, why should we expect this to why would a closed loop that doesn't intersect this discontinuity be acceptable? So why would a loop that does this be single valued? Well, let's try it out. Let's consider a loop that I write in the following way. So it has a radius which is just bigger than 1. Okay, so it starts here and it just goes outside here. It starts here, sorry, it's centered at 0 and it's just outside the two branch points. And we're going to play the same game. We take f of theta equals the square root of 1 plus epsilon squared e to the 2I theta minus 1. I've just plugged it in. Let me just remind you what the function was. The function was square root of z squared minus 1. So all I've done is just plug in that. Okay. And what do I get? I get this is equal to 1 plus epsilon, because there's a squared here, I can pull it out, e to the I theta, okay, and then I've got 1 plus e to the minus 2I theta. I've just divided the 1 by this, 1 plus epsilon squared, which I can now Taylor expand, and what does that give us? That gives us, again, squiggly lines, 1 plus epsilon e to the I theta, 1 minus, and then e to the, just take the leading order term, 2, 1 plus epsilon squared plus, and look, it's well defined. In other words, all of this, if you look here and here, it's completely well defined. We have that f of 0 equals to f equals to 2 pi. In other words, this branch cut here is perfectly acceptable, and any closed loop that does not intersect the branch cut is absolutely fine. Now, this is I just want to note something interesting, which is these look like two branch cuts, but you could think of them as basically the same branch cut on a Riemann sphere. So I'm going to draw this terrible sphere. Okay, it's going to something like that. And suppose now that, so this is the x, and this is the y, and this is the z. Okay, and suppose that I am, this is the x goes along here, and if I project up, the +1 branch point is here, the -1 branch point is here, and I could say that I said the first case that I gave you was that this one went out to infinity, so this line would go out to infinity up here, and the other one, -1, goes out to -infinity, but infinity maps onto the North Pole like that. So you could, it looks like one continuous line if we look at the Riemann sphere. Now suppose we just unfold this and just bring this down here. So I'm going to use a bit of color here. If I do that, this one could be just the same thing as that. Think of it as an elastic band which is pinned down to these branch points, and you can just move it wherever you want on the Riemann sphere. And it's just by looking at it in the Argand plane that it looks a bit odd. In one case it looks like two lines extending out to infinity, while in another one it looks like a finite line going from -1 to 1. But from the point of view of the Riemann sphere, they're very much the same thing. A useful concept in discussing branch cuts and points is the Riemann sheet or Riemann surface. Let's consider the following function, which you have seen before. We know that if we go around a closed loop, f of z will increase by 2 pi. And, you know, just look at it. F of z, well, let me rewrite this as, let me pick z equals to the I theta, and so f of theta is simply equal to I theta. Okay, and so if I go from f of 0 is equal to 0, but f of 2 pi is equal to 2 pi, even though z is equal to the same. Now, a way to think about this is to unfold the complex plane into an infinite number of sheets. So you take each sheet and you cut along, so you've got your sheet, right, XY, and you snip it along here, okay? And then what you do is you glue this side here to that side from the next sheet. And so then you go on to the next sheet and then you glue that side of that sheet onto that side of the next sheet. And what you end up with is what I've pasted here. It's like a corkscrew, like an infinite multi-story car park with a gigantic flaring corkscrew. And I say flaring because it goes out to infinity in the XY direction. So this is the Riemann surface tied to that function. And on that surface, on that Riemann surface, f of z, this f of z, i.e. log of z, is single valued. Now, take another example, which unlike this one, this is a kind of infinitely complicated, well, not complicated, but an infinite surface. You just made it very big. Let's consider a case where that isn't the case, but it has a strange topology. Let's look at f of z equals z to the 1/2, okay? And we know that if we write it in terms of r and theta, or r and phi, is r to the 1/2 e to the I phi over 2. So in this case, we start off in the same way. We take the plane and we snip this, okay? And all we need is 2 sheets. And what we do now is we go around, so we go around this, and when we get to here, we glue this bit to, this is the second sheet, to that bit of this sheet, okay? And so that glues onto that. And then we go around this, and this edge we glue onto here. So we glue these 2 sheets together. Now, there's no way of looking at this without it intersecting, but this is kind of a representation of what it might look like. In other words, you'll go up, it's one of these magical spaces where you'll go up a level, and as you go completely around in this multi-story car park, you end up emerging on the ground on a lower level. So this is the Riemann sheet or Riemann surface for the square root function and makes it single value.